but essentially, we often might do modeling with something as very simple as this kind of model, where we model the sprung mass, the chassis, and the bodywork as a big lump. We then model the unsprung masses, the uprights and the wheels and tires, and we model the tire just as a spring. And we have the springs and dampers of the car. Now, as a starting point, that's actually not a bad place to go. Somewhere like Red Bull will be much more complicated, but actually you can get a long way with that kind of modeling. And we'll put in a sine wave of increasing frequency called a chirp signal. And that will, as we do that, that represents a road surface quite well. And what we will then get out of these kind of results here, so we will get ride heights and we will get tire forces. And if we model the sine wave and we keep the velocity of the sine wave going into the contact patch the same, and the road height will come down because velocity is the differential of height, that represents a real road very well. You get high frequency bumps with very low amplitudes, and all the way up to very low frequency bumps, mountains, if you like, with much bigger amplitudes. So roads have a nice spread of everything, really. And what that does is when we put that sine wave through the model, we will see ride height and tire force characteristics like this, and you'll get these natural frequencies. So here at this point at about 5-6 hertz, we've got a heave mode when both the front and back of the car are going up and down together. And here at about 20 hertz on this particular vehicle, I've got a pitch mode. And you've got the front ride height in red and the rear ride height in blue. Now, it looks good here, the ride heights, because they're not moving around at the pitch mode. The rear ride height looks brilliant. Come and look at the tire forces. The tire forces are going up and down ballistically on the rear of the car on the pitch mode. So actually that's really bad, because the more variation in tire force we have, the less grip we have. And often in ride modeling work, we are looking for the best contact patch loads. So we often end up with quite soft damping. It's not too dissimilar to a road car. But what we might do is, having run that model, we will scan through a selection of different damping rates, which are on the x-axis here. And then we might look at, so the top two plots are contact patch loads, front and rear, and the bottom two plots are ride heights. And we will generally go for the damping that has the lowest contact patch variation, which enables us to get the most grip, basically. And if on the, somewhere like the rear here, where the best ride height and the best contact patch occur at the same time, that's very good. We more or less know where we want to go. On the front, it's here, this example, it's quite different, because the optimum damping for contact patch load is different to the optimum damping for ride height, which is way over here. So if I wanted to control the ride heights on the Formula One car, I'd be going very stiff damping. It's not a Formula One car, but on this car, if I wanted to get the best contact patch load, which is usually what I do, I'd go much softer damping. So the models, even quite simple models, can give you quite, get you 95% of the way there.